So let's give a warm welcome to Carmel High School, Team 7733. So the first question will be the easiest one to answer. Well, maybe they'll all be easy to answer. But tell us your name and what year you are in school, and then the judges will introduce themselves, and then you may make your presentation.
Good morning, my name is Miles. I am a senior at Carmel High School.
I'm Joe Filio. I'm also a senior.
I'm Simon Langowski. I'm a senior too.
I'm Tiger Huang, and I'm also a senior.
Good morning. I am Karen Bliss from Virginia Military Institute. This is Dan Connors from IBM and Ben Galuso from Shippensburg University. You'll have 15 minutes for your presentation. I will let you know when you've got 2 minutes remaining. I'll kind of give you a signal so you'll know that you've got 2 minutes left. Following that, we'll have 5 minutes of questions from the judges, and then we're done. So you can go ahead and get started.
All right, good morning. Cars are an integral part of American society. They provide transportation to the majority of people on a day-to-day basis. However, cars remain idle about 95% of the time, and furthermore, the transportation industry is responsible for nearly a third of the US carbon dioxide emissions. Our current models of transportation are unsustainable. So how does car sharing come in? Well, car sharing has the ability to reduce our impact on the environment, to improve usage efficiency, and to decrease our dependence on foreign energy. To evaluate the possibility of implementing car-sharing models, we took a three-part approach. First, we examined the typical commute. Next, we evaluated the viability of various models of car sharing, and then we tried to project these models into the future to see how they will change. This approach was applied to 4 separate locations across the United States. So first, let's take a look at the typical commute. Commutes can be classified based on distance and by time. Let's take a look at distance. The average distance traveled, we can say, is about the distance traveled crossing a city. The average distance for the 4 cities that we were given, the average width, was 8.25 miles, and we estimated that an upper bound for this category would be about 30 miles. Anything longer than 30 miles is a relatively long commute. So these are the divisions that we used for our distance bins. Next, let's take a look at time. We can say reasonably that a 10 to 30 minute commute is a fairly reasonable amount of time. Anything greater than that is a long time to be traveling in a car. This creates 9 cells for us to evaluate our population in. So first, we decided to look at distance. From a 2009 National Household Survey, we found that the average commute distance was short, and that distance dropped off fairly quickly. So we decided to use an exponentially decreasing model to model this distance. First, it was estimated that for every additional 4 miles traveled, about half the people would be about half as likely to make this commute. So this gives us the first part of our function right here. Next, we integrated this function and then scaled it down to have an area of 1 underneath the curve. This will allow us to calculate percentages directly by integration. So doing that for our distance bins, we get the following values. As expected, we see that the majority of our commutes are relatively short. Next, let's take a look at time. The challenge with looking at time is that time and distance are clearly not independent of each other. Longer trips will, of course, take longer amounts of time. So to combat this issue, we set up normal curves within each distance bin. This was determined using data from the Department of Transportation. So within the short distance bin, for instance, we set up a normal curve, and then we would use the cumulative distribution function for the normal model to find percentages in each cell. This gives us the following values shown here. Now, as expected, most of our commutes are still short in the 0 to 8.25 mile category. And we also noticed that there is a relatively strong correlation between the top left and bottom right diagonal. This is consistent with our earlier reasoning that longer commutes, of course, take longer amounts of time, and shorter commutes tend to take shorter amounts of time. Before we move on, a few key points. Earlier, we estimated that people would be about half as likely to travel an additional 4 miles. This was an estimate, but it could be better improved and fairly easily adjusted with better survey data. Also, to justify the use of the normal curves in our model for time, the duration of a commute is affected by a lot of random variables, including construction, weather, and traffic. Because it is impossible to predict exactly how these variables will affect the duration, a normal model was used, and we believe that because the positive and negative deviations are about the same, that this was a reasonable assumption.
So the second component of our analysis was to determine which of the 4 car-sharing models will generate the most participation among our 4 cities. So to solve this, we realized that the end result, transportation to a destination, was identical for all 4 methods, but the total cost was not. Thus, we could simply compare each method's explicit cost, how much money was spent, and implicit cost, the cost of time and convenience, and determine which model would be the cheapest. And because people are logical, especially over long periods of time, the cheapest car-sharing model would also be the one that would be most adopted. So to determine the cost of walking, which is probably the most glaring implicit cost, we used the utility function created by a 1967 behavioral economics study analyzing the placement of bus stations by Dominic and McFadden, and the later was actually a Nobel Prize winner in economics. So as you can see here, the utility function includes 3 variables: cost of transportation, time spent walking, and time spent in transit. Because each variable is first order, by finding the ratio of the total walking time coefficient and the transit time coefficient, we can determine that for every hour spent walking, people are willing to spend 3.3 hours and 35 minutes in a bus or in a car. Again, by finding the ratio of the total walking time coefficient and the transit cost coefficient, and then adjusting for inflation, we can determine that people are willing to spend about $24.32 to not walk for 1 hour. Having now found the implicit cost of walking, we then need to ascertain the maximum distance people would be willing to walk. Setting the cost of walking equal to the cost structure of the cheapest transportation alternative, which we found to be UberX, we found that logical people would walk for a maximum of 12 minutes and 30 seconds. At an average speed of 3.1 miles per hour, this translates to about 0.65 miles of walking. Before we utilize the conclusions of this function, we should note that it has several limitations. Those are some slides. So one of the limitations being that temperature and climate were not taken into account. When conditions are less than ideal, when it is flooding, raining, snowing, or tornadoing, people are less willing to walk. Depending on the location of the city and climate, this could be significant. Second, this model only describes 93% of household behavior, meaning that there are some people who are more or less willing to walk this distance. And then finally, this model was created in 1967, and it was published in 1975. Since then, it is possible that human willingness to walk has declined, but that was something that we were not able to take into account.
So next, we analyzed the 4 methods of car sharing we were asked to analyze. So the first method we analyzed was round-trip car sharing, which is essentially a rental car service. You go to the station, you take the car out, you go to your destination, and you return it at the end of the day. So the first thing we wanted to calculate was the average distance one would walk to get to the station to find the implicit cost of getting to a station. So for this, to account for the fact that you cannot walk through buildings, because first we did this using a circle, but you can't walk through buildings. You have to walk down streets. So if you want to go 3 units, you could go in a straight line down a street. But you could also go in a squiggly path, like this. And the set of all points that are 3 units away from the station forms a rhombus. So to find the average distance, we integrated the set of all possible starting positions that were 3 units away, for example, times that distance, and divided by this total number of all possible starting points, which is simply the area of the largest rhombus. We integrated from 0 to 0.645 because our utility function found that 0.645 miles was the maximum distance one would be willing to walk. Using this, we find that it costs about $4.70 per trip, or over the course of the year, $3,482. Combining this with the $23,000, the explicit cost of renting the car, we come out to a total cost of about $27,000. The next model we used was the one-way station model, which was an extension of the previous model. We made a few modifications to account for the fact that it was one way. you had to take 4 walking trips instead of 2 because you have to walk to the station on each end. And the explicit cost of renting the car went down because the hours you need to rent the car decreased because you do not need to rent the car while you are at your destination. This came out to about $17,000 a year. The next model was the one-way free-floating model. The one-way free-floating model utilizes super permits, where cars can park anywhere in the city. So we wanted to figure out how far you would have to walk to get to a car. So we used the city of Seattle as a model for our model. In Seattle, there are 660 cars in car-to-go service over 83.78 square miles, which gave us a car density of 7.88 cars per square mile. Based on this, we can expect that you will have to walk about 0.2 miles to find a car. So, using this, the result was that you had to walk, the cost was about $12,000. The last method, which is slightly different, or significantly different, is fractional ownership. We computed this as the cost of the car divided by the number of people plus the cost of gas. The cost of the car, we accounted for repairs, insurance, and the sticker price of the car using all the averages. And for the number of people, based on our research, we found that car sharing is usually done among 3 people. Assuming the schedules work, this came out to about $3,500 a year. Putting everything together in this bar graph, you can see that fractional ownership came out to be the cheapest method and therefore also the most adopted.
Okay, for the final part of the problem, we looked at how future changes in technology would change our models. And the main 2 technologies we looked at were electric vehicles and autonomous vehicles. So the first thing we looked at were the implicit pollution costs that came with every method. Because switching to electric vehicles would reduce this, it would eliminate that implicit cost. However, this is applied relatively evenly between all of our methods, so we could safely disregard this for this analysis. The next, for autonomous vehicles, we found that it caused our one-way station-based, one-way free-floating, and round-trip station-based all to collapse down into a single model we called the one-way hybrid. This was because of the self-driving nature of the cars, so there's no longer any cost to move the cars around. The cars essentially became their own jockeys, and this eliminated the labor cost, the need for stations and the cost for those, and also the walking cost since the cars could now meet the clients at whatever location they wanted to. We found that the cost of fractional ownership also decreased, and this was because of the reduced maintenance, because of the reduced mechanical parts, and also the reduced cost per mile driven because of cheaper electricity. While the cost for all of our methods went down, the margin between the fractional ownership and the one-way hybrid decreased.
So though we are happy that how well our model matched reality, in retrospect there are some tenuous assumptions that deserve discussion. So our distance function essentially states that drivers are half as likely to travel an additional 4 miles. While this works well for short and medium trips, it doesn't necessarily hold true for long trips. For instance, in real life, a driver is not half as willing to travel 104 miles as he is to travel 100 miles. In another iteration, we could use a piecewise function to better capture human behavior. Secondly, as of now, the free-floating model is only available in short distances, but our method of comparison requires each car-sharing model to provide the same service, which is transportation over short, medium, and long distances. Thus, for our analysis, we estimated the price of a free-floating model that did offer medium and long-distance trips. Finally, we assumed that there were no scheduling conflicts in the fractional ownership model. In reality, this seems unlikely. To better model our human behavior, we could try to deduce the implicit cost of scheduling conflicts, or we could try to reduce the number of people engaging in a fractional ownership agreement from 3 to 2, thus making the no conflicts assumption much more plausible. In conclusion, we found that the most commutes are short distance and short trips, in short time. We found that fractional ownership will be the most adopted car-sharing model under current conditions, and that when accounting for technological advances such as converting to electric engines and equipping cars with autonomous driving software, fractional ownership continues to be the most adopted model. Thank you for your time. At this point, we are open for questions.
All right. Well, thank you. Would you mind, you started to address it in your thing there at the end. Would you mind going back towards the beginning in question 1 and pulling up the distance distribution function again? Thank you. And the reason in particular, as you're getting there, is you identified the like a survey as informing you on creating that that function. Did the data provided in that match up with your model as it came out?
I think it worked particularly well for short and medium, as we pointed out. But
Right.
once you get to long, it really didn't. And we should have, in retrospect, used the piecewise function. I think when you look at it after 30 miles, it's pretty much very few people are going 30 miles if the half-life is 4 miles. So that was a shortcoming of our distance model, and it would be something that would have to be addressed for sure.
Okay, and you mentioned this too, but you were informed. It was the data didn't inform your decision for cutoffs. It was understanding of how the towns work that informed your cutoffs for distance.
Do you want to explain that for the
Right.
distance bins?
Yeah.
Yeah, just by city and then by inner city and so forth.
Mhm.
Yeah.
Okay.
So inside, the shortest distance was the length of the cities that were provided, the 4 cities. We found the average lengths, and then that was how we figured out our short distance bin.
Okay.
And then the long distance was more anecdotal, but what we thought would be across, like from city to city, as a reasonable estimate.
All right. Thank you.
I wanted to ask a question about the integral that you had
Yeah.
over a rhombus.
Yeah.
Can we see that?
You want to see it?
So this was inspired by like the shell method you use in calculus. So we applied that in 2 dimensions. But
So when I'm looking at that, I'm seeing sort of a discrete number of points that you could arrive at. And not, I guess,
Oh.
if you're on that diagonal from one city block to another city block, is it possible that there's going to be a car station in the middle of the building? I guess what I'm saying is I'm wondering here if a finite sum would be more appropriate than an integral.
we said the station was in the center, so then like if the line goes between the blocks, then you're inside the building, like if that's where your house is or your apartment, and then you'd walk out of your building in the shortest path to the road and then follow the road.
I see. Thank you.
See, I have a question on the kind of implicit cost of walking, and are people really going to factor that into their cost calculation? Do I know that I spent negative $3,000 a year walking?
Well, so in the study that was shown, McFadden and what was the other person's name? Well, the McFadden study, they did find that the model described correctly 93% of household behavior. So it did seem that people I guess maybe not they explicitly calculated, oh, this is going to cost me so-and-so money, but they did factor it into their decisions. And especially over longer periods of time, you see people, maybe not once again doing all the math and figuring out how much it's actually costing them, but, oh, hey, I don't want to walk in the rain every day. I should get a car,
And if I have a follow-up question on that one, in using that model, seeing how it's used for identifying the value of walking, for example, did it factored in the results showed that there were similar values for an output for all these cities. How is that reasonable? Or
Yeah, so that was in our model assessment, we
Right.
showed that was a shortcoming in that it didn't address climate, which would be, we thought, maybe a factor. Unfortunately, in 14 hours, we didn't have enough time to figure that out. And
right,
now-
I guess,
yeah.
are there other factors that I know you identified climate in that one. Are there any other factors that could make things differ between
Well,
these different locations?
The study. Oh yeah, the presence of public transportation may play a factor. Like a subway, then you'd be comparing the cost of a subway instead of UberX, so that would reduce the distance people would be willing to walk. But in terms of socioeconomic class or gender, race, everything, those are found to not be very significant in the study that we cited.
Okay.
Yeah, I have one more question. You mentioned early on that these car sharing are going to have an environmental impact. Can you tell me where and how that will happen?
So the premise behind, the motivation behind car sharing is to reduce the number of cars on the streets. So that has a twofold effect. First of all, it decreases the number of cars that we need to buy and that need to be produced in the first place.
Okay.
So the environmental costs of production will go down. And secondly, one of the biggest problems with congestion in big cities is the fact that cars remain idle. They sit in traffic for very long amounts of time, and that actually adds a surprisingly, that has a surprisingly large contribution on the carbon dioxide emissions. So by reducing the number of cars, the goal would be to reduce the amount of traffic and thus the amount of carbon dioxide emissions. So that would be the environmental benefit of car sharing.
Thank you very much.
Thanks.
Thank you.